Hello everyone, my name is Bindu MV and I am working as Associate Professor in Department of Mechanical Engineering, Louisiana College of Science and Technology. Myself along with my colleagues Professor Jairam B and Professor Siju K. Abraham is presenting a video on engineering mechanics on the topic Moment of Inertia. So in the previous video we have seen the fundamentals of moment of inertia. In this video we will see the derivation of moment of inertia of rectangular section and triangular section. So let us first consider this rectangular section. The width of this rectangle is marked as B and the depth of this rectangle is marked as D. So the centroid of this rectangular lamina, it is marked as the point G, and I have drawn two axes, one YY and the XX passing through the centroid, that is G. Now I am considering a small strip which is having a thickness of dy and that is at a distance of y from the centroidal axis. Now what is the area of the section? It is equal to dy into v. I can take the moment of inertia of this section about the centroidal axis. In that case, it will be equal to area into distance, that is y square. And if I integrate the moment of inertia of the small section throughout this limit, I can get the total moment of inertia of this rectangular section about the centroidal axis. So first, I can write the moment of inertia of the small section, that is Ixx is equal to y square into dA. What is dA? It is v into dy. Now I am integrating this with respect to the limit minus d by 2 to plus d by 2. That is Ixx is equal to integral minus d by 2 to plus d by 2 y square b into dy. So I can write it as b into y cube by 3, applying the limits d by 2 and minus d by 2, and expand the whole thing. I can write it as b d cube by 12. So the moment of inertia of a rectangular section about its centroidal axis passing through G, it is written as Ixx is equal to b d cube by 12. Now we will see the moment of inertia of the rectangular section about the y axis passing through the centroid. Now for that I am considering the same rectangular section with width b and depth d, and I am considering a strip which is parallel to the vertical axis and which is having a thickness of dx, and that is at a distance of x from the y axis. So the area of the strip will be equal to dx into d, and the moment of inertia of this strip with respect to the y-axis will be equal to area into x square. And if I integrate this moment of inertia with respect to the limit b by 2 minus b by 2 to plus b by 2, I can find the total moment of inertia with respect to the y-axis. So Iyy is equal to integral minus b by 2 to plus b by 2 x square b dx. So I can write it like this. So finally it is d by 3 into b by 2 cube minus b by 2 the whole cube, and finally I can write it as db cube by 12. That is the moment of inertia of a rectangular section about its centroidal axis passing through the centroid that is parallel to the vertical axis can be written as Iyy is equal to db cube by 12. Now let us see the moment of inertia of a triangular section. For that I am considering a triangle that is with this side capital B and this h height is equal to h, and the center of gravity or centroid of this lamina is marked here, that is G, and through that point I am having this axis here, and I am considering a small strip with B as the width and the thickness of the section as dy, and that is at a distance of y from an axis which is passing through the vertex R, and that axis is parallel to the centroidal axis. So I can find the moment of inertia of this section, that is the area of the section into y square about this axis, and if I integrate this with respect to the limit 0 to h, I can find the total moment of inertia of the triangular section with respect to the axis which is passing through the point R. That is dir is equal to y square into b into dy. So IR is equal to integral of 0 to capital H by square dy. But from this figure, I can write it as b by capital B is equal to y by capital H. So that means b is equal to capital B by H into y. So substituting the value of b in this equation, I can write it as integral 0 to h capital B by H y square dy, and finally applying the limits, I can write it as IR is equal to BH cube by 4. That is the moment of inertia of the triangular section about an axis parallel to the centroidal axis passing through the vertex. IR is equal to BH cube by 4. Now I can find the moment of inertia of this triangular section about its centroidal axis. If the moment of inertia of this triangular section about the centroidal axis is Ig, applying this parallel axis theorem, I can write it as IR is equal to Ig plus AH square. That is, Ig can be written as IR minus AH square. IR already we have found out, that is BH cube by 4. Now what is area? Area we can find it as half BH, and H means that is the distance between this point and this point. So what is H? H is equal to 2H by 3. This is a fundamental equation for central gravity of a triangle. This has been explained in the previous video by my colleagues. So this distance is equal to 2h by 3 and this distance is equal to h by 3. So substituting the value of h in this equation, I can finally write it as Ig is equal to BH cube by 36. That is the moment of inertia of a triangular section about its centroidal axis is equal to Ig is equal to BH cube by 36. Now we will find the moment of inertia of this triangular section about this axis PQ. Again I am applying the parallel axis theorem. IPQ can be written as Ig plus AH square. Here the distance will be the distance between this point G and the axis PQ, that is h by 3. So substituting this value, Ig is equal to BH cube by 36 plus half BH area, and h becomes h by 3 the whole square. Finally, I can write it as IPQ is equal to BH cube by 12. So the moment of inertia of a triangle about its base is equal to IPQ is equal to BH cube by 12, and moment of inertia of a triangle about its vertex is equal to IR is equal to BH cube by 4, and the moment of inertia of a triangle about its own central gravity Ig is equal to BH cube by 36. So in this video we have seen the moment of inertia of triangular section and the rectangular section. Thank you for watching. Thank you.